We are going to look at how to calibrate a delay generator with a data logger. Note this is a limited calibration, as well, it's a matter of opinion. I would argue that all calibrations are limited, just by a difference in the amount they're limited. Anyway, depends on your definition of limited, because it's not like we're checking every single thing 50 million times. In this case, we are going to check very carefully the delay from channel A to other channels. So I've put 2 seconds here. I could have written delay. I thought I'd write 2 seconds because it's just a bit easier to talk about, just because it's a real number. So suppose we generate a pulse on channel A, and then 2 seconds later we generate a pulse on each of the other channels. How are we going to know if the pulse really is 2 seconds later? Well, let's put it into a data logger. So clearly I'm assuming you've got a data logger lying around that you can use, and you want one which has got a calibrated time base. For the purposes of this calibration, we're not too concerned about the size of the voltage being produced by the delay generator, but just that it is producing a clear voltage and that the time is correct. So we need the time base of the data logger to be calibrated, because at some point any calibration process has to lead to something that is calibrated to, say, national or international standards. Okay, let's start looking at this in more detail. I'm just going to pick some numbers out of thin air, and then they'll make sense later. I think this is a better way to learn about it. Suppose we collect 12,000 samples per second. This is not arbitrary, it's a result of some maths which you'll kind of find out later. You don't have to understand the maths anyway, not totally. Okay, how many samples are there going to be in one that make up a single kind of delay? Well, we're expecting a 2-second delay, which means that's going to be 2 times 12,000 samples, which is 24,000 samples. So that's how many samples we're expecting to pass by before the second feature appears. That's a good number of samples, because that means we've got quite a lot of accuracy in our measurement. Exactly how much we're going to find out later. To get an idea of the accuracy, we need to know kind of how granular, or if we've missed something, how much have we missed it by. I'm going to change to a different colour to make it a bit easier to see. Let's look at what the minimum actual value is. Well, maybe the second pulse happened here, so I've just drawn it on the graph over here. Maybe it didn't appear exactly where we thought, but it appeared just after the previous measurement, so we just missed it. Well, in that case, that's how we get our minimum value, so it might be 1 sample length less. What about the maximum? I'm going to go to pink here. Well, maybe the final one did happen exactly where we thought, so this is worst case scenario. But then the first one actually happened really early. Again, we only just missed it. In that case, it's actually a little bit longer. It's longer by 1 sample length. So let's do some maths. This is just looking at the error here. If you're not too concerned about the error, or if this is your first go through the video, you might just kind of vaguely listen to this and then concentrate again in a minute. So the delay error, let's not write error, let's just say delay, because we sort of use shorthand here. The delay is going to be plus or minus, because a lot of people are going to be familiar with this terminology. So I'm writing the whole thing, then we'll talk about each bit. 1 over 24,000 times 100%. This bit here is a fraction. I'm saying that in a fraction we always say, what is it out of? Well, it's out of 24,000 because we're assuming that the delay is approximately 24,000 samples, and as a fraction of that total, it's 1 sample that we might be out by. It might be one sample too much or one sample too little. Hence, as a fraction, it's 1 out of 24,000. We times by 100 because that turns a fraction into a percentage. So that makes a percentage. Yeah, let's move on to the next page. The next page is a really kind of practical grid of what you might do. Let's pretend we've got a data logger. By the way, the data logger is limited to 25 million samples per second. This will become important as we go through. So samples, again, I'm not explaining exactly how I come up with samples per second, but you can probably guess you could just try and error this if you wanted. And later on I'll give it a way of working it out. 12,000 samples per second. How many samples will that give us in a pulse? Because that's important. That will give us an idea about sort of how accurate the measurement is for the pulse. Well, it's times 2 seconds. That gives us 24,000 samples. So I'm repeating the previous example. Bear with me, just so we get used to the grid. What is this error as a fraction? Well, we know that we might be out by one sample. It's that simple because we might miss either end by up to one sample length, because that's how often we're taking the measurements. So it's 1 out of 24,000. As a percentage, well, we times that by 100, and then I'm going to write this as a percentage. That is actually 0.00% if I round it to 2 decimal places. Now, let's pretend the data logger is accurate to 0.01%, the time base is. So it's just, in this example, I think it's good to illustrate that maybe the time base isn't perfectly known for the data logger, in which case the actual error is going to be 0.01%. What about 200 millisamples? Start speeding up it now. This would be 120,000 samples per second. How do I know? Because I kind of worked it out, or maybe I used trial and error. Is it okay if I just write that as 120k to save time? So we've got 120k times 2. Wait a sec, it's not times 2, it's times 0.2, because we need to times by the length of time. Guess what, that makes 24,000 as well. That is a magic number, it's quite important. The same maths is going to generate 0.00%, and once we take into account the error in the time base of the data logger, which we're pretending in this case is 0.01%, again we've got the same. What about 20 milliseconds? Well, this time we actually want 1.2 million. Which is, let's just write that out as a whole number just once so we can see what we're talking about. That many samples per second. So that's 1.2 m times 0.02, which guess what is 24,000. It's a number I tend to use. Gives me a bit of a margin. It actually rounds quite clearly as well. I'm not just cutting it really fine. Same numbers. We could do the same thing here. We could do 12 million. The same kind of thing happens and we end up with 0.00%. I'm guessing that as a viewer you probably don't want to keep seeing this done every time. Right, I am going to do this one, be careful, because something really interesting happens. Oh, we need 120 million samples per second. But wait a sec, we can't do that because we're trying to make this a real life example. What if we're limited to 25 million samples per second? So we've been forced to use a lower value. What impact does this have? So then that's 25 million samples. We times it by 0.0002, which gives us 5,000. Okay, so now it's 1 out of 5,000 as a fraction, which gives us 0.02% rounding to 2 decimal places. And let's add in the error from the time base of the data logger. If it's 20 microsecond delay we're looking to calibrate, well, we want to collect 1,200 million samples per second. Yeah, we still can't do that. The instrument hasn't changed, so we're still stuck at 25. So what's that going to do to the error? Well, you've probably made a prediction already that whether it's going to get worse. That's actually 500. It's not as bad as it's not as bad as you might. Well, it surprises me anyway. You're like, oh, actually, you know, still 0.2% accurate. Depends on your application. For a lot of people, that's fine. And let's say that's 0.21%. I'm skating over some more complicated statistics there about how you add errors. Let's not worry about that in this video. Let's call it 0.21%. It's not that bad, I guess. There you go. So there's a big picture. That's kind of how you do it. I'm going to talk a bit more about how you could pick the number of samples per second in a moment. That might not interest you. if you didn't fully get that, maybe just watch it through one more time. I've also got a website. I work as a consultant scientist. I also do some teaching and other bits and bobs as well, which is how come I started making these science videos, by the way. Anyway, find out more on the website, and there's a whole bunch of stuff about TCal, which is my calibration sort of product, a lot of which is just available for free download, because I'm crazy like that. Anyway, check out the website. Now, I'm just going to look a bit more detail, in a bit more detail, about how we decide on the percentage error. Let's suppose we collect K samples. Oh, we're going to do some algebra. So 1 over K times 100, because we want to turn it into a percentage. Let's suppose we want it to be 0.00% accurate. We need it to round to 0.00%. So I'm going to go for 0.0049. Because if I can get that level of accuracy, it's not 0, but we're never going to get 0 unless we collect an infinite number of samples. But that will round. When we round it, it rounds down to 0.00%. Blah, blah, blah. Let's times both sides by k, so let's just do a bit of algebra. So then we get 100 equals 0.0049 k. Stick a time sign in there if you like. Now let's divide by 0.0049, which gives us 100 divided by 0.0049 equals k, which means that k is 20,408. You might be asking, why did I use 24,000 earlier? Do you know what? That's just kind of what I've ended up using, because I don't like to cut it too fine, so it's a bit higher, and because of the way I'm often working with instruments and doing calculations fast when I'm working, I find that 24 is a really easy number to work with. If you're wondering why, because it divides by 2, it divides by 3, it divides by 4, it divides by 6, and it divides by 8, and it divides by 12. It's just a really easy number to work with. It means I can do sort of calculations of my head a lot more quickly, and so on. Anyway, if you're interested, that is actually why I use that number. But you could use any number greater than 20,408. And one of my top tips actually is, if you are doing work and you haven't like quintuple checked your working and had someone else check it over, I often double it. I haven't in this case, I'm pretty confident, but I might just double that to like 50,000, because that way if I was accidentally out by 2, then 2 years later I don't suddenly go, oh no, I'm going to have to redo all that work. Anyway, blah blah blah. Let's just do one more thing. Suppose you wanted it to be 0.0% only. Let's just change all these numbers. In that case, you only need 0.049, because that will round correctly, so then it becomes 0.049. And then we're only dividing by 0.049, and then that becomes 2041. Don't need as many samples if you're not trying to be as accurate. That's it. Thanks for watching. I'm available to do work. Check out my website. You'll find my contact details on there. I often get employed to take what you can see here and then customize it, or train a company up on it, something like that. And here again, I'm just leaving you with this overall grid. This is typically how I end up using it, so I can test a number of delays. And I'll often write all this out just so I'm really sure about what I'm doing on the day that I'm going to do some calibration.